Hello everyone. Thanks for inviting me to give this talk. I'm Muryel. I'm a third-year grad student at Johns Hopkins, working with Sylvia Gazzari. I'm going to present you this paper that we just got accepted on APJ on the systematic analysis of the X-ray emission in optically selected TDs. So as I'm the first talk, I'm going to do a very brief introduction. I hope everyone is familiar with this. So have stars in the galactic nuclei. The star is scattered towards a black hole. And if it's go inside the tidal disruption radius, it should get disrupted. And so part of the material is going to fall back into the black hole, a sharp rise in the fallback rate, and then a slow power law decay. And then if this forms an accretion disk, this should shine as a multi-temperature disk with an inner temperature of a few times 10 to the 5. But since the peak of the SED is the extreme UV, and that's unobservable, it should be most easily observable in the soft X-ray. And in fact, the first TD candidates were discovered in the X-ray by Rosetta, and in fact, the spectra were as expected, soft and with the temperature around that expected values. But we are now in the optical time domain era, and so most of the TDs are now discovered in the optical. The problem for this optically selected TDs is the optical unit UV emission is too bright to be produced by direct disk emission. Another problem is that most of the sources show no detectable X-rays in most of a large fraction of the sources. So instead of there's several different models on how you could make this different emission than the previously expected. I'm not going to go into details, but some of the open questions that arise from that is that, for example, how do you power this excessive optical emission in the optically selected TDs? It's reprocessing or shocks. And when does the direct disk emission dominate the luminosity? Does the accretion disk never forms in the sources that don't show X-ray, or they're just obscure? Which of the system parameters control this disk formation? And what's the relation between these optically selected and X-ray selected TDs? And what's the fraction of optically selected TDs that show X-ray emission or don't show X-ray emission? And also, what's the total rate of TDs? What's the relation between the rates in the X-ray and in the optical? So to try to tackle some of those questions, we performed this systematic analysis of the X-ray emission in optically selected TDs. So we basically selected all the TDs that were discovered between 2014 and December 2021. We excluded everything that could be an AGN and require X-ray detections. So that gives us 17 sources in this period. And then in terms of data, we had 2 big XMM programs led by my advisor, Sylvia Gazzari. And then we also used all the public data on ZTF, UVOT, XRT, and OGO, and Atlas. And then for the black hole masses, we have M sigma relation measurements for 13 of the sources. For the other 4, we use the galaxy mass. So we have an uncertainty of the black hole mass from this relation that is at best 0.4 DEX. In terms of the analysis, the UV optical, we did the standard single temperature black body fitting with the Gaussian rise in a power law decay, and then we also assume a plateau at late times because the source is plateau in the UV optical. And then for the X-ray, we fit the X-ray spectrum with a disk model where the X-ray should probe the inner part of the disk. We use Andrew Mummery model TD disk spec, where with that we measure the temperature, the radius, the inner temperature of the disk, the radius where this temperature is happening, and of course the X-ray luminosity. So we measured 3 things, but actually 2 are free parameters because they correlate with each other. So we have 2 free parameters from the X-ray. And so just to visualize this, at every epoch that's where we are measuring this LBB, I'm calling the integrated UV optical luminosity, assuming a single temperature black body, and the X-ray luminosity from the feeding of the X-ray spectrum. So just to make clear, none of these are the bolometric luminosity, right? This is not bolometric luminosity, this is not bolometric. Adding the 2 is also not the bolometric luminosity because we don't know, we cannot observe what's happening here. So some of the examples, of the sources, different evolutions. Assessing Fortune is a great example, one of the best studied sources. We have this power law decay and then plateau in the UV, and this kind of predicted power law decay in the X-ray emission. And then we can investigate the SEG shape by this ratio between the LBB, the integrated UV optical luminosity, over the X-ray luminosity. You see for this source, there's very little evolution, a little bit less than unit at early times and a little bit increase at late times, but not much evolution. And then a completely opposite example is 19 AZH, where you have this kind of same evolution in the UV optical, but the X-rays are completely different. At early times, it's very faint in the X-ray, but this is from the TD. This is a soft spectrum as you would expect, but it's very faint. And then at around 200 days after the optical UV peak, you have this rebrightening in the X-rays by a factor of almost 100. And then, again, the decay. So if you look at this LBB over Lx, you have very large values at early times, around 1,000, and then it decays around unity and maybe a few increase at late times. Another yet example of different X-ray evolution is exemplified by 18ZR, the first ZTF TD, where the X-ray luminosity is kind of flat the entire time at a faint level. So a few times 10 to the 41 at the entire evolution, maybe a little bit increase at late times, but not so much, not the same case of 19 AZH. And then again, if you look at LBB over Lx, you have this decaying value, but it actually never reached the same low values as the other sources. So, but if you look at the temperature, the X-ray properties, the parameters measured from X-ray feeding, the temperatures, regardless of the different X-ray evolution in the luminosity, the temperature shows the same trend in all the sources. The source is hotter at early times and then decays with time. Given the different X-ray luminosity evolution, that means that the radius that you infer from the feed are very different in evolution. So for assessing Fortune, you have this constant radius around the ISCO, so the unstable circular orbit. So this gray region kind of represents the uncertainty in the black hole mass. So anything in the gray region means consistent with ISCO. And so for these early times, epochs where the source is really faint but hot, this radius is really small. I mean, the inferred radius. And so it's so small that it's actually unphysical. And you can also see that in the relation between the X-ray luminosity and the temperature. For assessing Fortune, you have a perfect correlation between the two parameters. But for the other sources, these early time points here make the two parameters completely decouple. So these points and these points, the relation is not held anymore at these early times for these sources. So in terms of the entire sample, we have at least these three types of X-ray evolutions. A few sources show this power law decaying evolution. Most of the sources show this late time rebrightening. And a few sources show this like faint and constant evolution. So there's a large diversion in X-ray evolutions. Most of the sources do not follow a power law decay. And there seems to be a convergence of this LBB over Lx at late times to values around unity. So in all the sources at late times, they show kind of the same range of values. So as I said, the cooling of the inner temperature of the disk is universally present, independent of the X-ray evolution, of the X-ray luminosity evolution. So all sources that have enough points, they're hotter at the first epochs and cooler at late times. And as I said, that creates a problem for the early time estimated radius because they are much lower than the ISCO. So for all the other sources, yes, the X-ray follows the ISCO, the X-ray radius, but for these early times, for some of the sources, there's this problem here. And you can see, again, the same thing on the relation between X-ray luminosity and temperature. Several sources show some correlation between the two parameters, but then the sources that have that faint early phase, you have this completely uncorrelated relation between the sources, the parameters. So one thing we can ask is whether this late time rebrightening the X-rays means that there's a delay accretion, right? So if you just think that the X-ray luminosity follows the accretion rate, then that's the easiest explanation. One thing we can ask is whether the X-ray flux is actually tracing the accretion rate, because that's only happening if the optical path to the X-ray is optically thin. If you have something in the way, then that's not true anymore. Another thing, as I said, the early time radius seems to be unphysical, so there's something happening here. And the temperature is higher at early times. So if you go to the standard disk solution, the temperature should follow the accretion rate if you assume that the radius needs to be around ISCO. So you have a direct correlation between the temperature and the accretion rate. So actually, if you look at the temperature, the accretion rate is higher at early times, not at late times, even for the sources. So there's this incorrelation between the two parameters that creates some problems interpreting this. So there seems to be something much more complex happening here, and simple assumptions like luminosity follows the accretion rate may not be reasonable at these early times when there's the dynamic formation of the disk, there's the collision of the streams returning. So I don't think the things are just as simple as just saying X-ray luminosities always follow the accretion rate. So one thing we can check is the evolution of this, the spectral energy distribution shape as a function of time. So as I said, at early times, you have this wide diversity of LBB over LX, but at late times, shown by the black here, they converge to these values around unity. So one thing we did in the paper is try to answer how much LBB over LX can you produce with direct disk emission. So this is a set of simulations with different parameters, reasonable parameters for TDEs, the size of the disk, the inner temperature, and the temperature as a function of radius. And basically, the answer is that you cannot produce more than 50, a value of 50, with a direct disk emission. And so this means that these values here at early times are much higher, up to 3,000. As I said in introduction, this cannot be powered by direct disk emission at these early times. That's clear here from Assassin Fortune Lie in 19 ZH. Here I feed the X-ray spectrum and extrapolate from different radius of the disk. And so there's a range of possible emission for the UV optical of the disk. So there's always an excess of UV optical at early times. The case is much more problematic for 19 AZH than Assassin Fortune Lie, but still there's always excess. But at late times, here more than 200 days after optical peak, the SED seems to be consistent with the disk. So this is not a feed to the optical UV, it's just feeding to the X-ray and then extrapolated for different radius. We don't have great X-ray spectra at late times, so I don't have the same quality of data to do the same thing. So another way we can show this diversity early time SEDs is plotting the SED. So here, the three sources that I showed, Assassin Fortune Lie, 18 ZR, and 19 AZH, and also another source that show no X-ray emission. So you see this diversity in the spectral distribution at early times. And this is exactly what is expected by James I model, where these different SED shapes are given by a viewing angle. And then in a follow-up work by Lars Johnson, they show that at late times, depending on the angle, maybe not for the most edge-on case, you should converge to a disk SED at late times. Then the X-ray rebrightening is not caused by delay accretion, but because of the optical path to the X-rays is optically thick at early times and then becomes optically thin at late times. Not to say this is the correct interpretation, just saying that some of the things that are predicted in the model seems to be present in the data. So another thing we can measure is what's the fraction of optically selected TDs that show X-ray emission, right? So we select a reasonable threshold depending on the redshift and the instrument, so 10 to the 42. And then a control in uniform selected sample, the ZTF here, we just underselect our sample to only the ZTF ones. And then we just ask the number of sources that we have observations that are as deep as 10 to the 42 and the number of sources that we actually detect higher than 10 to the 42. And so that gives us 10 over 25. And then that means that the fraction of optically selected TDs that show X-ray emission higher than 10 to the 42 is at least 40% because our cadence is not perfect. So it could be more, but it could not be less than that. So another thing with this uniformly selected sample, we can ask if that X-ray loudness is dependent on the black hole mass. So here I show the cumulative distribution of the black hole mass for these two subsamples, and you see that there's no difference. Basically, there's no statistical significant difference in the black hole distribution for the sources, so the X-ray loudness in optically selected TDs is not dependent on black hole mass. And this is in agreement with previous findings, but here we have a control with a uniformly selected sample. Another thing we can do is compare these optically selected TDs with X-ray selected TDs. So here I plot the early time peak optical UV luminosity over the early time X-ray luminosity, and divide in three classes: the Rosetta discovered sources, the optically discovered with X-ray detection, so our sample, and optically discovered with no X-ray detection. So these are just limits. So what we can see here is that there's a continuous range, wide range of spectral energy distribution shapes, from 0.1 to 1,000. If you don't, we have the limits here for the sources in some of the Rosetta, but it's at least as wide as 0.1 to 3,000. So, and also there's no dichotomy between optically selected and X-ray selected TDs. There's a continuous range of properties in which each of the surveys is going to select preferentially from one of the ranges, but not exclusively. So for example, the source here didn't have early time X-ray emission, but was missed by ZTF and then was discovered by Rosetta at late times. So the service preferentially selects from a range, but it doesn't mean that there's two separate populations. Another way to think this is in terms of the rates. So we have now estimates of the rate of X-ray TDEs from Rosetta and a rate of optically bright TDEs from ZTF. And so we can think of two separate sets of sources. But as I showed you, these are not separate sets. They are one population that has an intersection. So if you think in terms of the rate intersection between the two rates is the constraint we have that it's higher than 40% of the optical. So the intersection between X-ray and optically is higher than 40% of the optical. So one last thing here is that combining our sample with Rosetta, XMM's LU, and Rosetta, we could construct a more fine detailed luminosity, X-ray luminosity function for our TDs. So this is not a survey, so the normalization here is a free parameter, so we renormalize to the Sazonov rate, but the shape can be constrained, and much better than was done by Sazonov because we have much fainter sources, have a more extended luminosity range. So we show that the luminosity function is better fitted by a broken power law than a single power law, and this break is fine around 10 to the 44 here. And interesting, this was predicted actually two years before by Andrew Mummery, that there should be a maximum luminosity for TDs in the X-ray at 10 to the 44. So, I mean, this is not a maximum luminosity, but you have a strong break from a power law of 1 to 2.5 at 10 to the 44. So TDs higher than 10 to the 4 in the X-ray should be extremely rare. So this also means that there's a large number of X-ray emitting TDs, but they're just too faint. These sources here, less than 10 to the 42, we usually cannot detect unless we point XMM Newton, and that's expensive. So for sources with XRT, we can only go up to maybe, for 10 to the 41, maybe up to 100 megaparsecs. So that's pretty rare. So this basically means that the rate that Sazonov et al. From the Rosetta sample calculated, which was a rate of TDs with luminosities higher than 10 to the 42.5, that's just a lower limit on the rate. There's a much higher, bigger population of X-ray faint sources that they miss out. So the rate that they have is actually a lower limit. There's many more results in this paper. It was quite a big paper that I don't have time to touch here. Things like differentiating AGN and TD with single epoch X-ray spectroscopy, hardness intensity diagram in TDs, accretion state transitions. We see the corona formation at least 3 sources at late times. And please check out the paper. The latest version was updated 3 weeks ago following the peer review. So thank you. Have to take any questions.
All right. Thank you for the great talk, Muryel. We have a couple questions already in the audience. I'm going to use my prerogative as chair to ask the first question, actually. Should be a quick one. When you were talking about the inclination dependent angle for your TDEs, I was curious if you see any indications of absorption in the spectra for the more X-ray faint TDEs, or if not, what limits can you place on that, and is it consistent with this picture where you're going through optical?
So the problem with that, if they're X-ray fainter, is hard to get detail in the X-ray spectrum. So it's basically not hard, it's impossible. So we've done now features in the X-ray for assessing fortune light, which is extremely bright, and then for 20 KSF, Thomas and I just had a paper on that, but at the late time, at the rebrightening phase. So it's really hard to do, basically. That's the answer. So we have no constraints on the faint ones.
Okay, yeah, I was just curious if the upper limits were at all constraining, but it sounds like
Yeah,
they're not really.
I don't think, yeah.
Okay, great. Let's start with Brian up here in the front. Oh, let me give you the microphone.
Thanks for the excellent overview. I was curious in regards to the ratio of X-ray to optical. Do you see any systematic trends with the black hole mass or proxy thereof? In other words, are the ones that are more optically or X-ray bright preferentially occurring in certain?
Yeah. So the thing we did is it was this, like, sources with X-ray peak X-ray luminosity higher than 10 to the 42 or lower than 10 to the 42, because that's a thing that we can actually like have a good number of sources in each. So if I divide in many more groups, like by LBB over LX, then I have too many groups and too few sources to do something meaningful, right? So that's the best we can do right now, is saying X-ray loudness or not, calling X-ray loudness something that is 10 to the 44, that is not correlated with black hole mass. And so that's...
All right. Thanks.
All right, I'm going to ask if you're sitting in the back of the room and you have a question, could you make your way to one of the two microphones so that people on Zoom can hear? I'll also say if anyone on Zoom has a question, please raise your hand so that we can see you in the room and we know to call on you. And in the meantime, I'll take a question right here.
Hi, I'm Megan Newsom. I'm a grad student here and at Las Cumbres Observatory. I may have missed it, but you mentioned the temperature evolution, but have you also looked into anything about like the softness and hardness evolution of the X-ray?
The softness?
Like, did the X-ray spectrum get softer over time?
Yeah, so that's one thing that I mentioned just here. So if the temperature is decreasing, then your spectrum is getting softer, right? But it's not because, for example, usually when we talk about hardness intensity diagram, we are talking about the formation of the corona, so that's a different thing. But when you're talking just the temperature, yeah, so if it's hotter, it's harder, but it's not as hard as when you have a corona, for example. So it's hard. But for the temperature, yeah, basically the temperature means the hardness in some sense.
I will take a question from over there.
Thank you. And you might just tell me to go read the paper, but I was curious if you could give me like a sentence or two synopsis about differentiating AGN and TDEs with X-ray spectra, because I'm really curious about that.
Yeah, so that's one of the plots we show there. So hardness ratio with X-ray luminosity, and this hardness ratio is measured. So soft is up to 1 kV, and then hard is higher than 0.1 kV. So TDEs are extremely soft because they don't have a corona. So it's quite easy. This is the BAT AGN survey. So the AGNs are dominated by corona, and the TDEs are not. But in some cases, you have late time corona formation, and so they can go at like something like here, but they are never hard as AGN. And the same thing if you feed the TDE with a power law, which is not physically correct, but you can do this to get this. So you can see the AGN corona is quite fixed at the point 1 to like 2.5. And TDEs are wild. They're extremely soft. So. Yeah.
Thank you.
Vikram, can you go to the mic?
Yeah, super fun results. I'm just wondering for all I may have missed this, but for all the results that depend on a single luminosity for each source, what do you assume? Like, what do you assume for the light, where in the light curve, what hardness ratio?
Yeah, so in most of the plots here, I'm talking about the peak X-ray luminosity, right? And sometimes I'm talking about the early time, so I get the first good X-ray spectra that we have, which is usually at early time, so we have some. So I'm not doing something very fancy like fitting the X-ray light curves because, I mean, the light curves are wild, as I showed. Yeah. It's hard to try to fit anything. So in some cases, I'm talking about the peak X-ray luminosity, and we have a good cadence for most of the sources. And for other cases, I'm just talking about the specific epoch, like as a time function. So at early times, at late time, at medium times, at late times. So it's usually how that's divided.
We should discuss further.
All right. If you can go to the mic, that'd be great.
Hey, that was a really nice talk. I had a question when you were showing the plots where you had estimated radius as a function of time. I guess it's kind of related to Vikram's question. Was that with the Mummery disk model that you were getting on physical radii?
Yeah.
Okay.
Yeah. So basically, it's quite easy to understand. Like, for example, 18ZR, you have 10 to the 41 with a temperature of 10 to the 6. That's less than ISCO, independent of the model.
Okay, got it.
Right? Like, it's even worse if you do a single temperature black body instead of a disk model. Which, that was a case in one of Andrew's paper, that with a single temperature, it's even worse. But even with the disk model, this is simply too faint and too hot to be.
If it was the peak of the, yeah.
Yeah.
Okay, but if you did, yeah. Okay, got it. Thank you. I just wanted to clarify the modeling.
Wenbin?
Yeah, can you go to the plot where you show the optical and the X-ray in one SCD and multi-panel, like 9 or 12 panels?
Let's see.
I think it's later. Yeah, here.
Here?
Yeah, so these disk models, do you just use the multicolor blackbody with the, do you use an outer radius?
Yeah.
So in order for the optical to be like a blackbody, you need to have some outer truncation at the, so what outer radii do you infer?
I think the range here, so the free parameter is the ratio between the outer and the inner radius. And so this range here is basically a range of outer radius. So I think that the smallest one here is like a ratio of 10 or 5. And then the bigger case is like a factor of a ratio of 100. So I'm exploring different sizes basically here. And so that's what this range means.
I see. So you can
So
actually
yeah, the
infer...
outer radius is a free parameter in this case. Yeah.
Okay. Thank you.
Not free parameter because I'm not feeding, but it's a parameter that you
can. It's something you can infer, right? If you
that's the thing that I'm planning is like actually feeding this at late times, like feeding the outer radius, but it's not in this work.
Thanks. Do you always find an outer radius or any time where you have just a multicolor blackbody without outer radius? It looks like it always overproduced, right? So there's always an outer radius. Looks like you're meaning the upper bound of your, which is a factor of 100.
Yeah. So this means that it's not as extended as a factor of 100, right? It's something in between the 5 and the 100.
That's right.
Probably the correct. But this is not a fit to the UV optic. That's something that I plan to do at some point.
That's right. Thank you.
All right, I think we have time for at least one more question, maybe two if it's quick. Yeah, if you can use the mic, that would be great.
So thank you for the talk. On this slide, I was curious, the delta T after the, I guess, is counted from the optical peak or?
Sorry?
The delta T where you
from
can,
the optical peak.
Okay. When you can actually use this single black body, this disk model to fit both the X-ray and the optical. Does it, this delta T, does it varies with the black hole mass?
The what?
Is a function of the black hole mass, like more massive have the shorter delta T?
Yeah.
Do you have enough coverage?
That much data to do that, like for a large sample sources. Maybe I have less than 10 sources that I can do something like this, like that I have a late time, good quality X-ray spectrum. At the same time, I have optical UV coverage. There's very few sources, so maybe 8. So that was not done yet, but like
you
I don't think
see
it's
any trend in the black hole mass.
Yeah, probably. I don't know. That's the answer.
Okay, thanks.
All right, I think we'll wrap it up there. Really quick question. Adele, can you come up and put your computer? We'll do one quick question while we change.
Okay, thanks. Yeah, so going back to the that plot where you've got the radius is too small. Yeah, next one. Yeah. So the implication here, to find that, then you have to assume that your X-ray model is, you've got a thermal disk and nothing else, so there's no Comptonization, which is causing you to get a false temperature, too high temperature, right? Yeah. And then so, assuming that's true, then the implication is that your X-ray flux is removed because of the absorption then, in such a way that you can't actually, so you don't see the absorption in the spectrum, but nevertheless it's there, and you're losing 10 or
I think that's, I think that is the case in this model, right? Like you take out some of the X-ray flux, and so your inferred radius is going to be smaller, but. Yeah, so, but you cannot see the features in X-ray spectra because it's faint, and so you have a very few counts to do anything. Yeah, but I think you're removing flux maybe, and then that causes your inferred radius to be too small.
Right. Okay, thanks.
All right, let's thank Muryel again. I'm looking forward to a lot more exciting discussions over the coffee break.